Okay, so let me just talk a little bit about homework here before I go on with anything else. Nothing, yeah, I decided to be lazy and leave the desks in place today. So I'll take your mission too once you get settled. But just wanted to take a second to look at the solution to mission 1 here with you. And mostly I just want to talk about notation. Because like most of probably the lion's share of things I wrote on your paper, and I didn't write too much, but that which I did write on mission 1, a lot of it's just about, just try to heads up about notation. So let me just try to like highlight some common wrong things I saw. So limit, right? I write limit of an expression, right? Nowhere ever have you seen me write limit not operating on something. I think that's true. Maybe if I, pretty sure that's never happened. So like, but you guys were like, some people with this might have written something like limit equal 42. And I understand what you're saying, right? But this is not proper notation, and we should write it limit of the expression we're operating on, right? And then the limit goes away when I go here because the limit's done, right? So I'm actually using a theorem about the continuity of this polynomial when I evaluate this function at that point, right? Now, you were not thinking of it as continuity of a polynomial at that point because we didn't talk about continuity back in mission 1, right? So I'm just kind of making a backwards looking comment there. So that's one of the main things is you don't get in the habit of just writing like limit equals stuff. It's always limit of a function, right? That's just notation. I don't think I really took off points for that this time, okay? So if you lost points, it's because the answers were wrong. It's not just about the work, okay? Like I would take off partial credits for like wrong notation on a test or something, but I try to be more forgiving on the homework, at least to start with. So like this one, if you didn't get infinity here, I probably took off a point, right? Because this one blows up to infinity as it happens. Now, just because you didn't write everything I wrote doesn't mean you didn't get full credit either, right? If somebody had infinity here without work, I would still give them full credit because I think that's not unreasonable to suppose that you could figure that out without actually writing anything down. Now, it's probably better if you wrote something down, right? You should try to understand why you had infinity there. But anyway. Now, let's see here if anything else pops into my mind. So that was the main thing, is just the notation is a little bit sketchy. The other thing is some people are using like arrows. So you might have had like this and then arrow that or something like that. And I try to only use arrows when I'm using an implication. If it's actually equals, then I try to write equals because it's it's better notation. It better describes what's happening. And the limit disappears once the limit is taken. Okay. So let's see here. So those are my main 2 comments. I think I don't think anything else pops out at me as particularly worthy of discussion. I think some of you got a low grade on this homework mostly because you didn't finish it, right? Like if you got a low grade, it's because you left a bunch of problems blank. So that probably won't happen in future homeworks. Also, do not despair. I mean, there will be bonus points to be had homework-wise later, right? I'll probably have like a bonus assignment at some point in the future, so you can kind of recover from the points you lost here. But do try to attempt all the problems, even if you don't get them all right. That'll be better for you. Let's see here. I would say this. There's one problem I had a mistake in the solution, which was this one, problem 14. And so I'm an idiot. Like, what's here is fine. This is all true. These are parts of the solution, but there's more. Because the other part of the solution, if I want greater than or equal to 0 here, equals to 0 is a solution. Like, just put in x equal to 0, it works. So 0 is part of the solution set, which I did not include, because 0 is between minus 1 and 2, right? So it's missing. So technically, I should say union the set just containing 0, because that's also in the solution set. And I was very happy to see one of you got that right, and I got it wrong. Like that, nothing makes me happier than when I find a correction to my solution in one of your homeworks. Like that, if that happens, I will give you bonus points. So, you know, these problems are what they are. I think a couple of you had this right, and a couple of you who didn't. It is what it is. This problem 16, I already told you problem 16 is not on the test, right? So this was just a homework exercise. The homeworks are generally harder than the tests, right? And not surprisingly, most people got problem 17, right? So I mean, you can copy, so that's good. So any questions about mission 1 now that I don't always go through the homework solution in here, but I thought for the first one I should at least talk a little bit about, like, so essentially if you have an X on the problem, that means it's mostly wrong, so I didn't give you credit. I don't give a lot of partial credit on homeworks. I just kind of, yeah.
Whenever we get like 0 for a limit, is it probably going to be like a negative or positive infinity?
You mean like 1 over 0?
Yeah, like I guess.
Yeah. Number 8. Let's see here. Let me go back. It depends on the nature of the limit, in a sense. But so this much I can say: if it's like if the numerator has a finite limit, but the denominator has limit 0, it's divergent. Like it does not exist. However, it could be plus infinity, it could be minus infinity, or it could be doesn't exist because it's both from both directions. For a one-sided limit, it's going to either be plus or minus infinity. This is a right limit, right?
Yeah.
So it's either going to be plus or minus infinity. This one's plus infinity because if we're a little bit to the right of 3, we're on like that part of the graph. If you want to look at the graph of y equals 1 over x minus 3, or you could think about plugging in like 3.1.
So
you know.
With this graph, if it didn't have like approaching 3 to the right, would that mean it doesn't exist then?
Yes, if it was the double-sided limit, it would be not exist because the limit from the left is minus infinity. And perhaps more interesting than all of that, of course, we should say this function has a vertical asymptote at 3, right? That's like geometrically what's going on. Okay, so oh yeah, you get to, once I give you your homework back, it's yours. You keep it. Yeah, I don't. Do you have a lot of classes here where you have to give stuff back?
No, yeah, also used to it
in high school. Oh, really? Don't they make up new homework in the next year? They just recycle the same one, so they can't give it back. Is that?
I don't know. I guess because like how I came up, they would have control of it.
Oh, they just keep all your stuff together. Well, that I could understand. See, I feel their pain. Like I've given back the graded homework of everyone who's here, right? But here's one that I couldn't give back today because this person's not here, right? And then there's another person who didn't turn in homework 1, right? So after a while, keeping track of all these exceptional cases, it does get old because I'll be carrying this around the rest of the semester until that person picks it up, right? Your high school teachers had the good sense to say, I'll just keep a folder with everybody's stuff in it. That way, they can't lose it. Shadrach? All right. And not one less thing to hold on to. Aha. So once you get settled, I'll take your mission 2, okay? All right, so are there any other questions about limit? Number 9?
Can we ask you about mission 2?
Let me grade it and then we'll talk about it. If there's a particular problem mission 2 we can talk about that.
Yeah.
I should say. Which one? Well, you think about it, and you asked about. I'll open it up here. Problem 9. Didn't get it.
Is it literally just plugging in? Because I got confused. I was like, my brain was.
Well, if we don't have a formula, all we can do is use the limit laws, right? So like here, I know I'm asked to calculate the limit of 7 times f of x, right? But one of the limit laws says I can pull 7 out, right? Pull a constant out. And then I'm left with 7 times the limit of f of x. But I'm told what that is. I'm told that that's 6. So the answer is 7 times 6, which is 42. The other one of the properties of cosine is that it's continuous. And what that means is you can pull the limit inside the cosine. But it's that's one of the ways I think about a continuous function. A continuous function is one for which you can pull limits inside the argument. Yeah. But anyway, so the point is the limit as x goes to 2 of f of x is 6, so I get pi times 6, which is 6 pi. Cosine of 6 pi is 1. So it does, yeah, it all goes back to the first one from mission 2. Sine of 1 over x.
Yeah, but when you wrote it out, it was like x squared, and it was like, I think, less than or that.
Mm-hmm.
So would you have, for that one, would you have put x minus 1 squared, what x squared was?
Yeah, I would start with what's true, right? What's true is that these chalk boxes are really hard to get into. Goodness gracious, it's so tight. Can only destroy this thing to get into it. There. So I would start with what's true, which is minus 1 is less than or equal to sine. I mean, we could write it this way. Here's an earlier step. I mean, this is the fundamental truth that sine of any angle in radians is bounded between minus 1 and 1. I mean, it's also true in degrees, right? But anyway, so of course I can replace that with 1 over x. Minus 1 here, that's what I'm interested in. And then I know that x minus 1 squared is greater than 0 for x not equal to 1, right? So then what? So since that's positive, I can multiply the inequality by that, and I get minus x minus 1 squared less than or equal to x minus 1 squared sine of 1 over x minus 1 less than or equal to, well, x minus 1 squared. And then the point is that the limit as x goes to 1 of plus or minus x minus 1 squared is equal to plus or minus 1 squared, which is otherwise known as 0. Thus, by the squeeze theorem, I can argue that the limit of the middle function also is 0.
It makes sense. I just want to make sure I didn't put the x minus 1.
Sure, sure. Other questions? Okay, so I said I was going to show you, or at least discuss, the proof of the intermediate value theorem. And my apologies to the person. Is there a person not? I think there's a person not here. Whoever's not here at the moment, because this projector and my camera, they do not play well together. I'm not sure what exactly happened here, but it's not, it doesn't look good. But everything I'm about to look at is in the notes, so you know, if you're watching the video, you can look at the notes instead. Okay, so intermediate value theorem is what I wanted to talk about. If I can get the view bigger here. So just a reminder, this is the intermediate value theorem. It says that if we have a function that's continuous on an interval a to b, and f of a is not equal to f of b, if n is a number between a and f of a and f of b, then there exists some c between those two numbers such that f of c is equal to n, right? So like here's a picture, this graph, here's like f of a, here's f of b, right? N I've drawn as the green dotted line. So for this function, there's not just one c. In fact, there's 1, 2, 3 places where f of c, 3 choices for c to make f of c equal to that n. So there's at least one, though, is what the intermediate value theorem says. Now, you can also use it to understand, let's see here. So I gave an example like this last class. You know, a polynomial, so I take this polynomial that's continuous on the reals. P of 1 is -1, P of 2, when you plug in 2, you get 12. So this polynomial goes from -1 at 1 to 12 at 2. That means between 1 and 2, there must be a value for which P of c is equal to 0. This is what the intermediate value theorem does for us. It helps us to be sure that there exists a solution to an equation. Well, if the equation is defined by a function which is continuous. Let's see here. Now, of course, you could actually open up a graphing calculator or whatever and zoom in and figure out exactly where that is. But I know it's somewhere in there between 1 and 2. We could find, you know, where the value, where there's a c such that P of c equal to 0, right? So I'll write that over here for a second. What was it? P of x. X to the what? 4x, is it 4x cubed? Plus 3x minus 2? Okay, so let me just, since they got the projector out here and playing around here, let me take a moment to look at something. So let's see here. So like this is Desmos, right? Here we go. So www.desmos.com, right? I have linked to this website multiple places in the notes if you read the electronic one, right? So I'll just look at y equals to, what was it? 4x cubed minus 6x squared. Fat fingered it. 6x squared plus 3x minus 2. And so as I was telling you, between 1 and 2, as you can see, it crossed 0 right there, right? Intermediate value theorem told me that that point exists, right? But I can use technology to actually zoom in on it and figure out where it is, right? Here's something else you could do that's fun. Check this out. X equal to c. Hey, wait a minute. Come on. Is c something? Why did it? Let me try something else. H. What on earth? Shouldn't do that. It's not asking me to. It's not behaving normally. Maybe I'm not connected to the internet or something. No? Usually if you put a letter like that, it'll say add slider. I don't understand why it's not asking me to add slider. Sure, whatever. Fine. Leave me alone. What? Uh-oh. All right. I don't know what's going on here, guys. That is very strange. I don't understand that. Now it lets me add a slider. Whee. So C is a parameter that you can control. I don't know why. Usually, like, it should let me put x equal to. It won't let me do. See, now it lets me do it. I don't know why it wouldn't let me do that before. But anyway, see, now it can look at x equal to, let me get rid of this one. So I just added that so we could look at the vertical line, x equal to c. And you can kind of see where it cuts through right there. And I'm just messing around. All right, let me put this away. I seem to keep losing people the longer I'm using this. Wait a minute. What did I lose? Nope, I still have 4. 80% of the class is here. Let me put this away here. All right. Ah! All right, so this graph here, I have graphed like y equals to f of t and y equals to g of t. So here f of t I think is let's see here, f of t is the blue one and g of t is the red one. As you can see, f of t is below g of t up to 1, and then f of t is larger than g of t beyond 1, right? And so you can ask the question, is there any place where f of t is equal to g of t? And the answer here can also be, the answer here is no. You could, and yet if you looked at h of t as f of t minus g of t, you could try to incorrectly apply the intermediate value theorem to that to be misled. See, if we look at f of t minus g of t, a place where this makes this function 0 would be a place where f of t is equal to g of t. All right, so we'll use this idea successfully in future examples. Let me not belabor it here. But so if the function f and the function g were continuous functions, and they satisfied this inequality that one was less than the other, and the other was less than the one over different parts of the interval concerned, then it stands to reason that there's a place where they have to cross somewhere. But if there's a discontinuity in one of the functions, you can avoid that necessity of the crossing. You can have just one jump past the other. But for continuous functions, that's not going to happen. But I mean, this example you can come back to later. All right, so let me just spend about 10 minutes of class here going through the proof of the intermediate value theorem with you. Maybe less than 10. I'll try to go fast here. But the first thing I do is I have this proposition 3.7.5. And what proposition 3.7.5 says, and so part of the reason I'm going through this proof with you is I think all the subparts of it have value in terms of increasing your intuition about what continuous means and just how we should treat continuous functions. There's some very useful facts that we discover along the way in this proof. This proposition is one of them. So this says that if you've got a continuous function and it's non-zero at a point, then if you're close to that point, it's non-zero. Like if you have a continuous function and its value is non-zero, if you're close enough to that point, it continues to be non-zero. That's what this proposition says. There exists some delta like that. And so the proof is actually not especially interesting. But basically you just pick epsilon as f of a over 2 and unfold this inequality to give you that, which allows you to make f of x larger than f of a over 2. On the flip side, if f of a is negative, you can choose minus f of a over 2. And if you make that your epsilon, because you can do that because it's continuous, then you can unfold the inequality from the definition of continuity to give you that f of x necessarily stays negative. So even the proof is a little bit interesting in the sense that it says if your function's continuous, if it's positive at that point, it has to stay positive close to the point. If it's negative at the point, it has to stay negative if you're sufficiently close to the point. Continuous functions can't just arbitrarily jump from positive to negative infinitesimally small. That leads us to what's called Bolzano's theorem. And Bolzano was one of these like monkish types. He proved the following. He said, let f be continuous. That's supposed to be a comma. Somehow it became a period. I don't know how that happened. Continuous on a comma b, such that the product of f, what does this mean? F of a, f of b less than 0. What's that say? The product of two numbers is negative. What can you tell me about those two numbers? Could they both be positive? Could they both be negative? Could they be 0? No, neither one could be 0, right? So that means it's either plus minus or minus plus. So that's just a sneaky way of saying that the sign of the function changes from a to b. So what this says is the sign of the function changes from a to b. Guess what? There's some point in between such that the function's 0. More often than not, this is how I apply the intermediate value theorem. I actually use Bolzano's theorem, which is this. Now, the proof here is actually largely based on the use of axiom 11 for the real numbers, which is that every non-empty subset which is bounded above has a least upper bound. And what I do in this proof is I define a set of values for the function which are negative, and I then argue that that set of functions is bounded above. That set of numbers is bounded above. And let's see here. And then, so since it's bounded above, the least upper bound axiom says that there exists an upper bound C, and in fact, that's exactly the C that we're looking for in the Bolzano's theorem, such that f of C is 0. So it's kind of sneaky, but the axiom 11 of the real numbers is what gives us the existence of this C. And anyway, I just want you to be aware of that. That's about as far as it goes. All right. So for what it's worth, guys, I borrowed this proof essentially from volume 1 of Calculus by Apostle. Apostle is a calculus book which is still being used in other parts of the world. Not so much here anymore because it's a pretty difficult book, and it's really not appropriate for this level of course. So anyway, that brings us to the intermediate value theorem. And to prove the intermediate value theorem, if you let g of x equal f of x minus n, right? So this function, if you have f of a not equal to f of b and n is between a and b, that will actually force g to change sign. So like f of a less than f of b means that f of a is less than n, less than f of b. So if I subtract n across this inequality, I get f of a minus n is less than, and this should be less strict inequality. These are strict. I shouldn't have less than or equal to there. So f of a minus n less than 0, less than f of b minus n. So that means that g of x equals to f of x minus n is a function which changes from minus to plus over this interval, which means I can apply Bolzano's theorem and get that there exists a c such that g of c is 0. But g of c being 0 is to say that f of c is n. So that's it. The critical and technical thing is the use of that least upper bound property. Now, moving on here, the last section in chapter 3 is also a little bit tricky, but essentially just speaks to the continuity of inverse functions. And so this is a proposition: S is connected and f from S to t continuous. F is 1 to 1 if and only if f is either strictly increasing or strictly decreasing. Do you guys remember what 1 to 1 property was? Remember what a 1 to 1 function had? It satisfied the what? Like this one does not satisfy the 1 to 1 property, because if I take this horizontal line, I cut through here and here. Right, so if I have f here, here I have f of a is equal to f of b, but a is not equal to b. So that's a violation of the 1 to 1 property. What can you tell me about that function? Is it increasing? Is it decreasing? I haven't carefully defined increasing and decreasing in here yet, have I? Yeah, I would say that it increases and decreases, doesn't it? So if this is A and this is B, it's increasing up to here, right? Increasing. I can't spell. Increasing. And over here, decreasing, right? But what this proposition says is that the function is 1 to 1 if and only if, and this is, I have to assume that the domain of the function is connected, so it doesn't get into any kind of shenanigans, but basically, if the function's 1 to 1 over some interval a to b, it has to basically look either like this or like that. It either has to be strictly decreasing or it has to be strictly increasing. All right? And so it turns out that the forward direction of this is just like pre-calculus argument. It's very easy. The reverse direction actually is really, really complicated and largely highly depends on the connectivity of the domain. I'm not going to go through this in class. It's not worth it. But I think you can agree with me this proposition is very geometrically obvious, right? Like it makes sense what this thing is saying. And then that leads us to Theorem 3.8.2, which says that if you have a function with a connected domain, all right, and this function is what I call the inverse function theorem here. If you have trying to find a way I can get it into the good part of the camera. If you have a function that goes from a connected domain to t, if it's continuous and it has an inverse, f inverse, then guess what? The inverse is also continuous. And the proof of this basically rests on that proposition I just told you, because the linking of the strictly increasing to strictly decreasing just to take a step back for a second. If the function's 1 to 1, you can define the inverse function. All right, that's just like basic function idea. So if it's strictly increasing, then that allows me to control inequalities, or strictly decreasing allows me to control inequalities. So basically, the fact that the function's invertible means it's 1 to 1, which means that it's strictly increasing or strictly decreasing on the interval. And because it's strictly increasing or strictly decreasing, I can control the inequalities I need to show that the inverse function is continuous. That's a summary of the proof that I'm not going to actually go through. Let me give you a more low-tech proof of this theorem. So how do you guys I'm going to come back to the proof of the theorem once I've shown you the results, because I want to put away the projector when I show you the proof, okay? But let's just go ahead here. So what does this give you? Like, what do you get from knowing that the inverse function of a continuous function is continuous? Well, you can do things like prove the continuity of the power function. X to the power p, how do you define that? Well, I don't know if you ever thought about this or not, but for p that's not like a rational number, we can use a logarithm to define the power function. So well, I'll talk more about that in the chalkboard. Let me write that out. I just wanted to get to the point here. So the result is just what we want. The polynomial, rational, power, trigonometric, hyperbolic, as well as the respective local inverse functions are continuous on the interior of the respective domains. So all I'm saying is, just like last class, just lumping more sort of logs onto the fire. If you have inverse functions that you can plug in the point in a reasonable way, you can also do that. The continuity of the inverse functions is also true. So let me put this away. Now, I should have warned you to wipe off your desk. I was standing, your desk. I was standing there earlier. Oh, it's working now. Yay. This didn't work earlier. I had to stand up on top of the table, unplug it, and then plug it back in because, I took like a 2-year degree in IT training, and the thing I learned was that you should unplug and plug things. That's actually a lie, but it's not far from the truth. Like, the first thing you should do is unplug and plug things, right? No? All right. Reboot, right? All right, come on. You can do it. Go to your home. There we go. I gotta go order some more dusty chalk because this dustless chalk, it just doesn't hardly shows up. All right, so guys, so my question for you is, how's the graph of y equals to f of x and y equals to f inverse of x related? And we talked about this before, but I'll remind you now. If AB is in the graph of f, that's true if and only if BA is in the graph of, that was supposed to be graph, what happened? Of f inverse. So let's see here. For example, sine. This is the sine. This is y equals sine x, right? 4 minus pi over 2 less than or equal to x less than or equal to pi over 2, right? So if we restrict our attention to sine from minus pi over 2 to pi over 2, this is an invertible function, right? Because it's 1-to-1. It satisfies the horizontal line test. And what does the graph of the inverse look like? Well, so this point here is minus pi over 2. Come on. Minus pi over 2 minus 1. This point up here is pi over 2, comma 1, right? So the inverse function, you flip-flop those. So it's like down here, right? Minus 1 minus pi over 2. And this one flips to, yeah, up here somewhere, right? Right. And then essentially, if I can, I don't know if they cross or not. I can't remember. I'm trying to, well, we did in a proof of something else. We mentioned that the line y equals x. Remember, we needed to use that the opposite value sign of x is less than or equal to opposite value of x to prove the continuity of signs. So like I know that y equals x is above this and it's below that. So I think actually if my picture was right, it would kind of be like that. So good grief, I can't think. I can't. Well, this point is on the graph of the inverse function, right? And this one, I guess, has to flip to that one, right? So you can draw the graph by like sort of like reflecting across the line y equals x, right? So the graph of the inverse function looks something like that. Anyway, I'm just going back to this to remind you, how do we draw the graph of the inverse function? You draw the graph of the inverse function in the same way you draw the graph of the function, except what? You trade the roles of y and x, right? So just think about that for a second. If the function's continuous, it must be that the inverse function's also continuous, because if you draw the graph of the function, it's got no jumps in it. If you draw the inverse function in the same way, it should also have no jumps in it, right? So that's not a careful proof, but it's certainly an argument that should show you it's very plausible that what I'm saying is true. All right, so see if I can find my rats. So let's look at an example. Now that we know continuous functions are I was about to say, now that we know continuous functions are continuous. That's not a very good sentence, is it? Now that we know inverse functions are continuous, let's look at an example. So here's the question. Does inverse tangent of x equal to minus cosine of x? On, say, minus 2 to 2. So at first glance, like you might be like, well, I don't see how that, I mean, I have theorems about functions, right? So how do I solve an equation? Well, to solve an equation using our theorems that we have, we're going to change the equation so that it looks a little bit different. We're going to say, well, this question is equivalent to the question, can we, if we let f of x equal to, say, tangent inverse tangent of x plus cosine of x, right? If we look at this function, does have a 0 on minus 2 to 2, right? If this function, if we can find f of c equal to 0 for this, right? What happens if f of c equal to 0? That would be inverse tangent of c plus cosine of c, right? So if you could find such a c, that would be exactly what you're looking for, right? Because then inverse tangent of c would be equal to minus cosine of c, which is the desired outcome, right? Okay, so observe f of x equal to inverse tangent of x plus cosine of x is the sum of continuous functions. Right? Because now we have the inverse function theorem that says, since tangent is continuous, the inverse function to tangent is also continuous. And cosine is continuous. We went through the details of that before. So we have a continuous function. So we can apply the intermediate value theorem. So consider what's f of minus 2 equal to? Inverse tangent of minus 2 plus the cosine of minus 2. What's the f of 2 equal to? Well, that would be inverse tangent of 2 plus the cosine of 2. What are those equal? What do those work out to? Plug it into your handy-dandy calculator, and what you will get is about minus 1.52 for the first one. And you get about 0.691 for the second one. Right? So what's that tell us? Well, yeah, those are not where it's 0, but we can see that this is a continuous function. Right, so since f of minus 2 is less than 0 is less than f of 2, the intermediate value theorem says what? There exists a c in minus 2 to 2 such that f of c equal to 0. Hooray. And for what it's worth, if you examine the graphs, if you like plot, I mean, so that intermediate value theorem is never going to tell us what the value is without some nuancing of it, without some finesse. It just tells us that there exists a solution. To actually find the solution, what do we need to do? Some kind of numerical method or something, right? So like this one, how I usually do something like this is I would just graph them. You know, inverse tangent looks like this, right? Minus cosine looks like what? So cosine starts at 1, right? Minus cosine starts at minus 1. Basically just flip-flopping cosine. Oops, it doesn't go that high. I don't know. It's cosine, so it's stuck between minus 1 and 1. So this where cosine is 0, it's this is like pi over 2. Or minus pi over 2, that's where cosine is 0. And if we did this, if you did it more carefully, you can see that probably this is this at least there's one solution here for sure. Right? That's what C actually is. It's like right there. And in fact, what I say in the notes is that if you use technology to look at the graphs carefully, you can actually find out that C is about minus 0.82. So that's, by graphing with calculator. With technology. What? It's like, okay, well, some of these things will not erase. That's interesting. What's going on there? And that brings us to the end of my chapter 3. All right, that's everything pretty much I have to say about continuity of functions. And so that brings us, of course, to what I usually think of as being, in some sense, this is the real start of calculus. I mean, limits are a necessary evil, in my view, in this course. But what we're about to do is, I think, far more interesting. So I now want to talk to you about tangent lines. So this is the start of chapter 4. So we talked about this before, right? At the start of the limit chapter, I explained to you we needed to look at limits of type 0 over 0 because the tangent line necessarily involves that. So I won't go through all of that again, but I'll just do this. If this is the function, right, graph of the function y equals f of x, and we want to describe the tangent line to a, right? We can look at, say, a plus h, and construct the secant line through there, and then think about the limit as h goes to 0 to get the tangent line, right? So the tangent line, well, first of all, f prime of a is equal to the limit as h goes to 0 of f of a plus h minus f of a divided by h, if this limit exists, if the above limit exists. We say f is differentiable at a, and it has tangent line y equals to f of a plus f prime of a times x minus a. So the tangent line is something like that, right? It's the line whose slope is chosen such that the tangent line just kisses the graph at that one point and then kind of bounces off. We can calculate the slope of the tangent line by taking the limit of the difference quotient, like so. That's what we're going to be doing for the next day or two. So that's one way you can calculate the slope of the tangent line. I should mention that there's another way we could do it using a limit with x. And we'll get back to that. But first, let's do an example which uses the current notation, okay? So example 1. Let's look at f of x equal to x squared, all right, minus 1. X squared minus 1. And I want to find equation of tangent line through 1, 0. Does that make sense? I mean, we can only find the equation of the tangent line at a point which is on the graph. Is 1, 0 on the graph of this f of x? What's f of 1 equal to? 0. So that's good. First, you should always double check me on stuff like that. Every so often I'll write a question that just doesn't make sense. It has happened. Okay, so let's calculate f prime of 1 then. We need to find the slope of the tangent line. f prime of 1, it's the slope of the tangent line. You can also say it's the derivative of the function at 1. These are both true. Derivative of f of x at 1. I usually use a equals to 1. But anyway, so we need to calculate f prime of 1. Hopefully it exists, right? Limit as h goes to 0 of what? Of f of 1 plus h minus f of 1 divided by h. What is f of 1 plus h here? I have to do what? This is composition. I have to put in 1 plus h in the place of x. 1 plus h quantity squared minus 1. That is this piece right here. All right? And then I have to do minus f of 1, which was, we just talked about it, 0, right? I mean, you don't have to write the 0 down technically. I'm just pointing out that that term is straight up 0 because that's the value of the function there, right? And then I divide by h. Mm-hmm. I'm calculating what is f of 1 plus h. That means I have to evaluate the formula for f with input 1 plus h. So just putting 1 plus h for x. Does that make sense? Mm-hmm. Okay. Now I have to work it out. What do we got? Well, not 0. 1 plus 2h plus h squared minus 1 divided by h. Now the 1's cancel, and we could factor an h out of the numerator, right? I'm almost at a chalkboard here, so I'm going to just go ahead and say that that's 2 plus h, right? So the 1's cancel, and we can factor h out, and then h cancels with h. Indeed, that equals 2. Now, that's not the answer. That's part of the answer. I asked what the equation of the tangent line was, right? So we know this much. The slope of the tangent line is 2. So how do I find the equation of the tangent line? Well, go back to how I defined it right here. I'm supposed to take f of 1 plus f prime of 1 times x minus 1, right? So this tells me that y is equal to 2 times x minus 1 is the equation of the tangent line. Because remember, we use y equals to f of a plus f prime of a times x minus a. This general formula becomes that in this context because f of a was 0, I mean f of 1 was 0, and f prime of 1 was 2. So the equation of the tangent line is 2 times x minus 1. Let's take a second to graph it. So the graph here, I think we can graph everything in sight, right? This is pretty low-tech stuff. The parabola, it has x-intercepts of plus or minus 1, right? So this is y equal to x squared minus 1, which, by the way, is x minus 1, x plus 1, if you want to get fancy. So that's how I knew that this was minus 1. And